The second equilibrium podcast is about gas phase equilibrium and reaction quotient. Now in the last podcast we put all the values in K in molarity. You can do that for a gas phase reaction. You can also put the values in pressures, and we don't call that K anymore, we call it Kp. So Kp is still products over reactants like K was, except that your values are all pressures of gases. You still raise those values to the power of their exponent. So NH3 on the product side raised to the power of 2 because of the coefficient of 2, and then that all over the pressure of nitrogen raised to the first power, and hydrogen raised to the third power because of the coefficient of 3. These values within the Kp are all equilibrium partial pressures. Now we can easily convert from the Kp to the K and vice versa by the equation that you see on the screen. The Kp is equal to the K, that's the value that you get when you use everything in molarity, times the gas law constant times the temperature in Kelvin, and that whole RT raised to the delta N. And as you can see on the screen here, delta N is the moles of gaseous product, so you take the coefficients, so the example above would be 2, minus the moles of gas reactants, so in the above equation that would be the 3H2 plus the 1N2, so that would be 4. So you would be taking the 2 from the NH3 minus the 4 from the other side, so that would give us a negative 2 as the exponent on the RT. Now if your reactants and products have the same number of moles in the equation, gaseous moles, then the Kp and the K are actually equal to each other. Now you can have a heterogeneous equilibrium, and that's an equilibrium where you have not just gases or not just solutions, but you also have solids and pure liquids present. The position of the equilibrium and the determination of the K value has nothing to do with those pure solids and liquids, because they don't have a concentration, because they're pure. You have a pure solid, you can't really calculate the concentration. You have a pure liquid, you can't really calculate the concentration. So you actually leave those out of the equilibrium expressions. So in this equation that you see on the screen, because the PCl5 is a solid and the PCl3 is a liquid, you exclude those. When you write the expression, it's still products over reactants, but you only put in the products and reactants that are gaseous. So in this particular case, your K is going to equal Cl2 concentration, and if you were doing this in pressure values, your Kp would simply equal the pressure of Cl2. So notice the PCl3 and the PCl5 are left out completely. But again, they can't really change, they don't have a pressure, and they can't really change in concentration because they're pure. Now when dealing with equilibriums, there is a variable called the reaction quotient, and this Q, otherwise called the reaction quotient, is basically K, but not at equilibrium. So this example should look like the example in the first podcast. You have the balanced equation, capital letters are the substances, lowercase letters are the coefficients, and the Q is simply products raised to the power of their coefficients over reactants raised to the power of their coefficients. So essentially Q is the K value, but the values in the expression are not necessarily at equilibrium. Now, why do we do this then if the Q is not at equilibrium? It's actually to determine whether the system is at equilibrium, or which direction the reaction would have to go more in order to achieve equilibrium. So the first situation, if the Q, the products over reactants not necessarily at equilibrium, does equal the K for that particular reaction, then you know the system is at equilibrium. If the Q is greater than the K, then the system will actually shift to the left to achieve equilibrium. So it's going to go back towards the reactants to achieve equilibrium. And then the third situation, if the Q is less than K, the system is going to shift to the right to achieve equilibrium. So when it shifts in the second and third case, you're trying to get that Q then to equal the K value. So the shift occurs in order to get that Q equal to the K.